ASHRAE 90.1-2004 limits the lighting power density. This means that the actual lighting load for the building needs to be calculated first. To calculate this load, you multiply the total square footage of the building by the watts per square foot. In this case it is 340,000 square feet multiplied by 1.1 watts per square foot, totaling 374,000 watts. The code does not force the use of specific volt-amps per square foot values for sizing the service. Instead, it requires that the service be sized based on the actual connected load. In this case, the actual connected load is 374,000 watts. There is no specific rule of thumb for sizing the service for a courthouse. However, based on the actual connected load of 374,000 watts, a reasonable service size would be approximately 600 kV, assuming a diversity factor of 0.625. Diversity factor is a ratio expressing the probability that all connected loads will not be operating at their maximum simultaneously. It accounts for the fact that not all electrical equipment in a building will be running at full capacity at the same time. The code does not require the use of 3.5 volt-amps per square foot for office areas or 2.0 volt-amps per square foot for courtrooms if the actual lighting load is lower. The service should be sized based on the actual connected load, which in this case is 374,000 watts. A reasonable service size based on the actual connected load would be approximately 600 kV-amps. Sizing an electrical service involves several crucial steps to ensure the building's electrical needs are adequately met while adhering to safety standards and regulatory codes. Firstly, determine the total connected load. This involves calculating the power consumption of all electrical equipment and devices that will be connected to the electrical system. This includes lighting, HVAC systems, appliances, computers, and any other electrical loads within the building. Secondly, apply demand factors. Demand factors account for the fact that not all electrical equipment will be operating at its maximum capacity simultaneously. These factors are typically provided in the electrical code or can be estimated based on a building's occupancy and usage patterns. Apply appropriate demand factors to the connected loads to determine the maximum demand load. Thirdly, consider future expansion. It's essential to anticipate future electrical needs and incorporate additional capacity into the service size to accommodate potential expansions or increased electrical loads. This can prevent the need for costly upgrades in the future. Fourthly, calculate the service size. Once the maximum demand load is determined, calculate the required service size in amps. This can be done using Ohm's law and considering the voltage of the electrical system. Ensure that the service size is adequate to handle the maximum demand load with sufficient safety margin. Fifthly, select appropriate equipment. Choose electrical equipment, such as service entrance conductors, circuit breakers, and transformers that are rated to handle the calculated service size. Ensure that all equipment complies with relevant electrical codes and standards. Sixthly, coordinate with the utility company. Consult with the local utility company to determine the available service voltage and capacity at the building site. Coordinate the service design with the utility company's requirements to ensure a seamless connection to the grid. Seventhly, ensure compliance with codes and standards. Adhere to all applicable electrical codes and standards, such as the National Electrical Code or local built-in codes, throughout the service sizing process. This ensures that the electrical system is safe, reliable, and compliant with regulatory requirements. Eighthly, consider energy efficiency. Incorporate energy-efficient technologies and design practices into the electrical system to minimize energy consumption and reduce operating costs. This can include using LED lighting, high-efficiency HVAC systems, and smart building controls. Ninthly, provide adequate grounding. Ensure that the electrical system is properly grounded to protect against electrical shock and equipment damage. Grounding systems should comply with electrical code requirements and be regularly inspected to ensure their effectiveness. Tenthly, document the design. Maintain detailed documentation of the service sizing calculations, equipment specifications, and system design. This documentation is essential for future maintenance, troubleshooting, and upgrades to the electrical system. Remember, accurate load calculation is paramount for electrical service sizing. Accurate load calculation is paramount for electrical service sizing, ensuring the electrical system can handle the building's demands safely and efficiently. It involves several steps. Firstly, identifying all electrical loads entails cataloging every device and system drawing power. This includes lighting, HVAC, appliances, and machinery. Each load's power consumption is recorded in watts or volt amps. Secondly, determining demand factors is crucial as it accounts for simultaneous usage. Demand factors, specified in electrical codes like the National Electrical Code, estimate the percentage of total connected load used at any given time. Applying these factors realistically prevents oversizing the service, which can lead to unnecessary costs. Thirdly, calculating the total demand load involves summing up all individual loads after applying demand factors. This figure represents the maximum power the electrical service must supply. It forms the basis for selecting appropriate service equipment. Fourthly, accounting for non-continuous and continuous loads is essential. Non-continuous loads operate for less than 3 hours, while continuous loads operate for 3 hours or more. The National Electrical Code requires continuous loads to be factored at 125% of their rating, ensuring the service can handle prolonged operation without overloading. Fifthly, considering future expansion allows for scalability. Anticipating future electrical needs, such as additional equipment or increased occupancy, prevents premature service upgrades. Adding a buffer to the calculated demand load accommodates these potential increases. Sixthly, using appropriate software and tools streamlines the process. Electrical design software and load calculation tools automate complex calculations, reduce errors, and ensure compliance with codes. These tools provide detailed reports and facilitate accurate service sizing. Seventhly, documenting all calculations is necessary for transparency and future reference. Detailed records of load calculations, demand factors, and assumptions support design decisions and aid in maintenance or modifications. This documentation demonstrates compliance with regulations and facilitates troubleshooting. Eighthly, consulting with electrical engineers is advisable for complex projects. Their expertise ensures accurate load calculations and appropriate service sizing, minimizing risks and optimizing electrical system performance. Engineers consider all relevant factors and provide tailored solutions. Ninthly, reviewing and updating load calculations is essential as building conditions change. Modifications to equipment occupancy patterns or energy efficiency measures can impact electrical demand. Regular reviews ensure the service remains adequate and efficient. Tenthly, considering voltage drop ensures efficient power delivery. Voltage drop occurs when power loses strength over distance. Accurate load calculations help determine conductor sizes to minimize voltage drop and maintain optimal equipment performance. A comprehensive load calculation process ensures the electrical service is appropriately sized, promoting safety, efficiency, and reliability. Remember that safety margins are crucial for electrical service sizing, providing a buffer to handle unexpected loads and ensure system reliability. Several factors contribute to the importance of incorporating safety margins. Firstly, handling unexpected loads involves accounting for unforeseen electrical demands that may arise due to new equipment or increased usage. A safety margin ensures the service can accommodate these loads without overloading. Secondly, accommodating load growth is essential for long-term reliability. Electrical demand tends to increase over time as buildings expand or occupants add more devices. A safety margin allows for future load growth without requiring costly service upgrades. Thirdly, preventing overloads and faults safeguards equipment and personnel. Overloads and faults can occur due to equipment malfunctions or wiring issues. A safety margin helps prevent these events from damaging equipment or causing safety hazards. Fourthly, ensuring voltage stability maintains consistent power delivery. Voltage fluctuations can affect the performance of sensitive electronic equipment. A safety margin helps maintain voltage stability, ensuring equipment operates reliably. Fifthly, complying with codes and standards mandate safety margins. Electrical codes, such as the National Electrical Code, specify minimum safety margins for service sizing to ensure compliance and safety. Sixthly, improving system reliability reduces downtime and maintenance costs. A service with adequate capacity is less likely to experience failures, reducing downtime and maintenance costs. Seventhly, mitigating risks associated with inaccurate load calculations prevents undersizing. Load calculations can be complex and prone to errors. A safety margin helps mitigate the risks associated with inaccurate load calculations, preventing the service from being undersized. Eighthly, providing flexibility for future modifications allows for adaptability. Buildings may undergo renovations or modifications that require additional electrical capacity. A safety margin provides flexibility to accommodate these changes without requiring extensive service upgrades. Ninthly, extending equipment lifespan minimizes replacement costs. Operating electrical equipment within its rated capacity prolongs its lifespan and reduces the need for frequent replacements. A safety margin helps ensure equipment operates within safe limits. Tenthly, enhancing overall safety protects occupants and property. A properly sized electrical service with adequate safety margins enhances overall safety by reducing the risk of electrical fires, shocks, and other hazards. Incorporating safety margins into electrical service sizing is a prudent practice that enhances safety, reliability, and long-term performance. Remember that dating factors must be considered. Dating factors are essential considerations when sizing electrical services. Firstly, ambient temperature impacts conductor capacity. Higher ambient temperatures reduce the current carrying capacity of conductors. Dating factors adjust for this effect, ensuring conductors operate within safe temperature limits. Secondly, conductor bundling affects heat dissipation. Bundling multiple conductors together restricts heat dissipation, increasing conductor temperature. Dating factors compensate for this effect, preventing overheating. Thirdly, conduit fill affects conductor cooling. Higher conduit fill percentages reduce airflow around conductors, increasing temperature. Dating factors account for this, ensuring conductors remain within safe operating temperatures. Fourthly, voltage drop influences conductor sizing. Excessive voltage drop reduces equipment performance and efficiency. Dating factors help select larger conductors to minimize voltage drop. Fifthly, harmonic distortion impacts neutral conductors. Nonlinear loads generate harmonic currents that increase neutral conductor loading. Dating factors account for this effect, preventing neutral conductor overheating. Sixthly, altitude affects equipment cooling. High altitudes reduce air density, decreasing equipment cooling efficiency. Dating factors adjust for this effect, ensuring equipment operates within safe temperature limits. Seventhly, equipment duty cycle influences service capacity. Intermittent equipment operation allows for lower service capacity compared to continuous operation. Dating factors account for this duty cycle, optimizing service sizing. Eighthly, conductor insulation type affects temperature rating. Different insulation types have varying temperature ratings. Dating factors ensure conductors operate within their insulation's temperature limits. Ninthly, load diversity influences service demand. Not all loads operate simultaneously. Dating factors account for this diversity, reducing overall service demand. Tenthly, code requirements mandate dating factors. Electrical codes specify dating factors for various conditions. Compliance with these codes ensures safe and reliable electrical installations. In conclusion, considering dating factors is crucial for accurate electrical service sizing, ensuring safety, reliability, and code compliance.